Hello guys. Last time we were talking about constructing antiderivatives or a whole family of antiderivatives graphically. Today what we're going to do is we are going to introduce some notation to represent that family of antiderivatives. Again, they were just vertical shifts, or algebraically they had that plus c at the end. And then we're also going to introduce some basic formulas for antiderivatives. Later in the course, in a couple of lectures, we'll start developing some fancier formulas analogous to the quotient rule, the product rule, et cetera, et cetera. But for now, we're just going to do some basic formulas. So first off, the integral of f of x dx represents the family of antiderivatives. So this guy is different from before because we don't have any bottom or top. Before that was called a definite integral. This, on the other hand, is an indefinite integral. An indefinite integral. Because we're not actually evaluating a particular number. A number is not going to come out of this. We're going to get an entire family of functions out of this. So let's do some examples. Say we want the integral of x dx. Well, once again, this represents the entire family of antiderivatives. So first off, can you think of a function whose derivative is x? Hopefully you said x squared over 2. Because if I take the derivative of x squared, I get 2x, and the 2's cancel. But this is representing the entire family of antiderivatives, so I need to say x squared over 2 plus c. And again, that plus c is just representing all possible vertical shifts. So I'm going to put up two more examples. So here are two more examples. I'd like you to pause the video, give them a shot, and then I want you to come up with a general formula for the integral of x to the nth power dx. So give those a shot. Hopefully you wrote x cubed over 3 plus c, because the derivative of x cubed is 3x squared, the 3's cancel. And x to the 4th over 4 plus c. Again, the 4 comes down if we take the derivative, and we're left with an x cubed there. So if we look here, it looks like we have a pattern. The 2 becomes a 3, the 3 becomes a 4, and if you think about it, there's a hidden 1 here. So you can think of this as x, or x to the 1st. And in all these cases, what we're doing is we are winding up with x to the n plus 1 over n plus 1. Right? The 1 becomes a 2 over 2, the 2 becomes a 3 over 3, the 4 becomes a 4 over 4, plus c. This formula, I think of this as the reverse power rule. So you guys remember the power rule from differential calculus? That's where we took the derivative of x to the nth power. Now we're trying to find the family of antiderivatives. And I do have to say one thing. This formula works great except for one particular case. So pause the video and see if you can think of what case. Hopefully you said the problem is that n can't be negative 1. Because if n is negative 1, that formula falls apart. It won't even be defined. So that's the first formula that I want you guys to have in terms of a way to find a family of antiderivatives. And I'm going to write several others on the board. Actually, I'm going to put them over here because this is where I want to have my final formulas. The integral of e to the x dx, the integral of cosine of x dx, and the integral of sine of x dx. So please pause the video, give it a shot, see if you can come up with these general formulas. Hopefully you said e to the x plus c, because the derivative of e to the x is e to the x. Hopefully you said sine of x plus c, because the derivative of sine of x is cosine of x. And hopefully you said negative cosine of x plus c, because the derivative of cosine of x is negative sine of x, so we need another negative there to cancel out the negative. So these are some basic formulas. There's one more basic formula that I want you guys to be aware of at this point in time, and that's the integral of 1 over x. Or the integral of 1 over x dx. Now notice this actually takes care of my -1 case here, because x to the -1 is 1 over x. So that's the one that we're going to study now. Before I write this one down, take a second, see if you can guess what that is. So hopefully most of you said, oh, that's just the natural log of x plus c, because the derivative of the natural log of x is just 1 over x. Well, it turns out that it's not quite right. It's almost right. I claim that the answer should be the natural log of the absolute value of x plus c. So this one's a little bit weird, because the derivative of the natural log of x is 1 over x, but when I integrate 1 over x dx, I get the natural log of the absolute value of x. So why is that true? So let's prove it over here. Well, I'm going to case this out. Before I even case it out, let me tell you what I'm going to try to do. I need to convince you that the derivative of this guy is this guy. Okay, if I do, then the integral of 1 over x dx is the natural log of the absolute value of x. Well, what I'm going to do is case it out in two cases, because the absolute value of x is a little tricky to work with when we're talking derivatives. Hopefully you remember it's not differentiable at the corner. So if x is bigger than 0, then the derivative of the natural log of the absolute value of x, again, I'm hoping to get this guy out. Well, if x is bigger than 0, the absolute value of x is just x. The reason for this is that absolute value does nothing to positive numbers. And then we know from differential calculus that the derivative of the natural log of x is 1 over x. So that case is satisfied. If x is less than 0, the derivative of the natural log of the absolute value of x is the derivative of the natural log of what? Well, what happens if x is less than 0? What does the absolute value do to that? Well, let's take a look. If I have the absolute value of -3, I get out 3. But saying I get out 3 isn't very mathematical. What exactly am I doing to the -3 to make it turn into a 3? And the answer is, I'm taking that -3 and I'm multiplying it by -1. I'm taking the opposite of that. That's the mathematical operation. So if x happens to be a negative number, then the absolute value of it is going to be the opposite of that number. It's going to be the natural log of -x. If you're a more visual person, let's just study the absolute value of x for a second. So if x is bigger than 0, we're on this side, and we spit out the line y equals x. The absolute value of x is exactly equal to the line y equals x. If x is less than 0, the absolute value of x spits this guy out. Well, what is this guy? This guy is y equals -x. So that's how you can see that visually. So at this point, I invite you to stop the video for a second and finish off the proof. Hint, use the chain rule. Okay, now that you're back, the derivative of the natural log of stuff is 1 over stuff times the derivative of that stuff. That's the chain rule. Again, as a reminder, it's been a while. The derivative of f of g of x is f prime of g of x times g prime of x. So that's f prime. So the derivative of the natural log of stuff is just 1 over, that's the f prime business, the inside guy, times the derivative of the inside guy. Note, if this is foreign to you, you definitely want to review it. It's going to pop up this quarter. But anyway, continuing this, 1 over negative x times negative 1 is in fact 1 over x. So if x is bigger than 0, we get 1 over x. If x is less than 0, we get 1 over x. And if x equals 0, we could care less because this thing is not even defined. Therefore, since the derivative of this is this, the integral of 1 over x dx is equal to this guy plus c. There are a couple of additional properties that I want to list. And these properties are just analogous to what we saw in the world of definite integrals. So in particular, the integral of f of x plus g of x dx is the same thing as the integral of f of x dx plus the integral of g of x dx. So in other words, if you want to integrate a sum in terms of this indefinite world, then you could just do them term by term. And finally, the integral of c times f of x dx is equal to c times the integral of f of x dx. And I mean, the proofs of these, the integral of this is just going to be some function big F of x plus some function big G of x plus c. Actually, let me actually write that down. So if I go to this side, the integral of f of x dx plus the integral of g of x dx. So I'm going to show you guys something. This is going to be f of big F of x plus, let me say c1, plus big G of x plus c2. So again, each of them is adding all possible constants. So what we always do is, if you think about this, if you add together any possibility of those two constants, you can just mush them together into one constant. So hopefully you've seen that in one of your science classes. So that's what this is. But if I just went directly from here, this is exactly the same thing as the left side. So again, the power of this is this means that we can just look at things term by term, and this means that we could pull out constants. So let me show you some of these in action with a couple of examples. Keep those properties up there for reference. So example, I want the integral of 6 u to the x dx. By that property involving constants, I could just pull the constant out. So just as with derivatives, the constants can go along for the ride. So it's just 6 times whatever this guy becomes. And this guy becomes e to the x. I'm going to do it a very careful way first, and I'm never going to do it this way again. But sorry, let me write out all the details. It becomes 6 times the integral of e to the x dx, because we pulled the constant out. And then this becomes 6 times e to the x plus c, which is 6 e to the x plus 6c. But if this c is representing every possible real number, and you're taking 6 times every possible real number, then you can just mush these guys together into just one constant c. So from now on, I'm not going to do it like this. I'm just going to do whatever work I need to be done here, and at the end, I'm going to slap on a plus c. So let me give you guys a couple of additional problems to try out. And I'll get out of the way in a second. Probably can't see this. So I'd like you to try both of these. Give these a shot. pause the video, and then when you've given it a shot, come back online. All right, so let me go through this now. I actually just need this one, and we'll see why in a second. Well, first off, this looks like a quotient. We actually don't have a quotient rule yet. You had a quotient rule with differentiation, and actually it turns out we will never have a quotient rule with integration. However, we do have this reverse power rule. So one powerful thing about mathematics is our ability to transform tougher problems into problems that we actually know how to solve with a little bit of manipulation. So 5 over x cubed I can write as 5 times x to the minus 3. So that's properties of exponents. So in other words, 1 over x cubed is the same thing as x to the minus 3. If you can't remember your properties of exponents, you definitely want to review them. So let me finish this problem, and then I'll put them over here, and maybe you can practice them, do a Khan Academy video, or search online for more practice. But getting back to this problem, we now have it in a form that we can deal with. The constant, again, goes along for the ride. And x to the minus 3, well, we just need to add 1. So I get minus 2 and divide that by that. So we get 5 times x to the minus 2 divided by minus 2. So again, I just want to take 2 seconds to remind you guys about some potentially helpful exponential properties, because this is how we want the thing to look. So we might need to navigate some things that kind of look like that, but only after we use the properties. So we have x to the minus n is equal to 1 over x to the n. That's a good property to know. X to the a times x to the b equals, actually I'm going to write them out without giving away the punchline. Let's see if you guys remember them. Those are good. And let's do 2 more. Actually, sorry, let's do 3 more. That one is helpful. And finally, right, so these are your exponential properties that pop up here and there. Let me give you guys a minute, work them out, see if you can remember them. And then press play on the video. All right, hopefully you said that we just add exponents if we have the same base. The idea here is that we've got x, a of them, times x, b of them. So we have a total of x, a plus b of them. So that's why that's true. When you divide and you have the same base, that's x to the a minus b. X to the 0 is equal to 1. Xy to the a is x to the a times y to the a. The reason why that's true is this is really xy. You've got a of them. In other words, you've got a of the x's and a of the y's. Analogous to this property is that x over y to the a is x over a, x to the a divided by y to the a. And then finally, x to the a to the b is x to the a times b. And the idea behind this is x to the a means you have x. So you've got a of them, and you do that b times. So you have a total of a times b x's. All right, if I were you, I would pause the video for a minute, try to do the second one now that you kind of have the tools, and then press play. All right, let's check this guy out. I'm going to work it out up here. Well, we know that the integral of a sum is the sum of the integrals. In other words, I could just take care of this guy, integrate it, take care of this guy, integrate it, and then add them together. So that's what I'm going to do. So let's see. Well, before I even get there, though, I don't have any product rule. There's no product rule. So I need to use one of the rules that I have already. And I can do that by realizing that the square root of x is just x to the 1/2. So that's x to the first, and hopefully you see where that's going to go in a minute. But let me play the same game here. This is 1 over x times x to the 1/2 dx. Well, over here we could just add the exponents. 1 plus 1/2 is 3/2, so it's x to the 3/2. Right? That was one of the exponent properties. So same thing here. This is 1 over x to the 3/2. Again, we don't have a quotient rule, but this is the same thing as x to the minus 3/2. Integrating then, this becomes, we can integrate this guy, and then add. So this becomes x to the 3/2 plus 2/2, or 5/2, divided by 5/2. But if you divide by 5/2, that's the same thing as multiplying by 2/5. And I'm always going to do that with fractions. If I make this x to the 5/2 over 5/2, we're dividing by a fraction, so you can just flip it. And I will do that always. It just looks cleaner. So that's this first piece. So if I have the second one, I have x to the minus 3/2 plus 2/2, or x to the minus 1/2, divided by minus 1/2, which is the same thing as times minus 2. And then finally, I want to add my c at the end. So in summary, in this lecture, what we did is we developed some basic formulas that we can use to come up with the family of antiderivatives. And in future lectures, what we're going to do is develop more sophisticated tools so that we can deal with more complicated functions.